lesson, we will introduce recursive sequences, which are not as bad as they seem, although they do have a tendency to frustrate a lot of kids. So just stick with it, and we'll see how it goes. So consider the following sequence: -8, -2, 4, and 10. What are two ways that you could calculate the 10th term of the sequence? Well, the first thing I could do, obviously, is I could just keep adding 6, right? So the first term, second term, third term, fourth term. So just go 6, 7, 5, 6, 7, 8, 9, 10, and just keep adding 6. That would be one way that I could get that 10th term. The second way I could do it is I could just write the equation, right? We know that the 0 term would be -14, so I would get the equation t of n equals 6n minus 14. I could plug 10 in and get 60 minus 14 is 46. So either way, I would get that 10th term. And again, the 10th term is 46. If you've not already done so, write the equation. This is known as an explicit equation, which is going to be a little bit different than recursive equations. Explicit equations essentially say, hey, look, I want to know the 10th term, so I can go straight to it. Explicitly go straight to it. Recursive is what we did up here, which essentially says, hey, start at this number and then add 6 each time. So it says, and this is where we get a little bit of trouble, the term after t of n is called t of n plus 1. So imagine, if you will, we have this sort of situation, and to just kind of go through this real quickly, and hopefully we won't get too lost in this. That was not good. I guess I should have made that white. That might be better. Okay, so if I'm at term t of n, this is the term I'm on right now. If I want my next term, I'm just going to add 1 to that. And this is basically means next term. And if I want the previous term, I'll say n minus 1. And if I said something like t of n plus 2, which I probably wouldn't, I'm essentially saying 2 terms from now. Because everything is based off of n, right? So if I add 1 to n, so imagine if I say t of 2, well, that's this term, t of 2. What's the next term? Well, what's 2 plus 1? It would be t of 3. And what would be t plus 2? It would be t of 4. And what would be 2 minus 1? It would be t of 1. So right now I'm talking about t of 2, but if I want the next one, I add t of n plus 1. So this t of n and t of n plus 1 is going to be a big deal. This is really going to be kind of the beginning of our recursive sequences. Now, the t of n plus 1 will come up a little bit, not really. It'll actually be a of n minus 1. But I really want to hone in on this t of n and t of n plus 1 right now so that we can sort of move ahead a little bit. So, oh boy, I have all of the stuff I should get rid of. It would have made a lot more sense to have just reopened this, but I feel like I'm pot committed at this point. All right, so let's go ahead and keep moving then. So if we want to write this explicit equation, the next term after t of n is called t of n plus 1. So write an equation to determine the value of t of n plus 1 if you know what t of n is. An equation that depends on knowing the previous term is called the recursive equation. I'm going to tell you right now, recursive equations always start like this. T of n plus 1 equals t of n. Always. We're going to say, hey, look, if you want the next term, take this term and do something to it. What do you want to do to it? You want to add 6 to it. That's what this recursive equation is. So it says Alejandro uses recursive equation t of n plus 1 equals t of n plus 6 from part C of problem 572 to write a sequence and came up with the following. And you can see why I would do this, right? 0, 6, 12, 18, 24. We're just adding 6 each time. Does the sequence match the sequence from 572? Nope. They do both add 6, but it's a different sequence. So what is he missing? He's missing a starting point. So in a recursive sequence, not only do we say, hey, look, we always start with t of n plus 1 equals t of n, then we say, how do you want it to change? Well, then we give you a starting point. Hey, by the way, the first term is -8. So you should start at -8, and then you should start adding 6. That way, here, he started at 0. It was the wrong place to start. So if Alejandro did not make a mistake using a recursive equation, why did he get the different sequence? Because he didn't have a starting point. So that's what we need to do, is go correct that. So let's go ahead and take a look then at some of these recursive sequences, and let's see if we can make sense out of them, because like I said, I know a lot of kids get frustrated with these, but they're really pretty simple. So Avery and Colin were trying to challenge each other with recursive equations for sequences. Avery wrote this equation. Help Colin write the first 4 terms of the sequence. Well, I know the first one is 3. It's given to me, right? T of 1 is 3, right? This is my n and my t of n. So if I want the next term of the sequence, if you want the next term, so if I want term 2, that's the next term, because right now I know 1 is 3. So if I want the second term, take this term, 3, the output of this term I should say, 3, square it. 3 squared is 9, minus 1 is 8. So now I am at t of n is 2. The output is 8. So if I want the next term, which is the third term, take the output of this term, which is 8, and square it. 8 squared is 64, minus 1 is 63. And then if I want the fourth term, and thanks for doing this to me, I need to square 63 and then subtract 1. So I'm going to get 3968. So that's how that sequence is going to work. Is this thing arithmetic, geometric? It's other. How do I know? Because it's not adding by 5 and it's not multiplying by the same number, so it's got to be other. Describe to Colin how you could create the 10th term of the sequence. And here's what's so important about recursive sequences. How do you get the 10th term of the sequence? Well, you're going to have to calculate the 9th term. Well, how do you get the 9th term? You have to calculate the 8th term, and so on, until you get back to, no, I'll just square 3968 and subtract 1. I'll square that, subtract 1, square that, subtract 1. Sort of like dominoes, right? Recursive sequences are sort of like dominoes in that regard. It doesn't ask us to calculate the 10th term, so I'm not gonna. All right, now Avery and Colin are still at it, so we're given this one. T of 2 equals 19. So again, I have n and I have t of n. I know that t of 2 is 19. And it's saying if you want the next term, which is 3, if I want the next term, the third term, I take this term, 19, and I subtract 2 from it, so it would be 17. And if I want the fourth term, I'm going to take the output of the third term, which is 17, and subtract 2 and get 15. So you can see it obviously works backwards like this. So it says help him write the explicit equation. Well, the explicit equation would be t of n equals minus 2n plus 23, right? If I want the second term, I plug in 2 here, and I get 19. If I want the fourth term, I plug in 2 here, and I get 15. And again, that's proven recursively, like a domino, and it's proven explicitly by plugging in. Is this sequence arithmetic, geometric, or neither? It's arithmetic. It's adding a -2 or subtracting 2. Then Avery wrote 6n plus 8. Help Colin write a recursive equation. Okay, so we have n and t of n, right? We know if we plug 0 in, we get 8. If we plug 1 in, we get 14. If I plug 2 in, I get 22. I'm sorry, that's not true. I get 20. If I plug 3 in, I get 26, and so on, right? So if I want to write this recursive equation, they all start like this. If you want the next term, take this term and add 6 to it. But by the way, start, and again, t of 1, not t of 0, t of 1 is 14. So start at 14 and then start adding 6. So you can see how you can go back and forth between the recursive and the explicit equation. Let's go ahead now and open up 523b, and finish this off. So we have this Fibonacci sequence, super famous pattern. It appears many times in mathematics. It can describe patterns found in nature, such as the number of petals of flowers, the arrangements of seeds in sunflowers, scales of pine cones. Super interesting. You should actually Google it after this. Pretty crazy how often it appears in nature. It is named after Leonardo of Pisa, who is known as Fibonacci. He introduced the sequence to Western European math in 1202, though it has been discovered earlier by others, including mathematicians in India. So here's the Fibonacci sequence. The first term is 1. So again, we have n and we have t of n. The first term is 1. The second term is 1. If you want the next term, right? If I want the next term, take the output of the previous term, or of this term, and add it to the previous term. So 1 plus 1 is 2. If I want the next term, take the output of this term and add the output of the previous term. So if I want the next term, I'm going to add these two together, and so on. I guess I'll continue my table for a while so we can see. So if I want the 6th term, I'm going to add the 5th and the 4th output. If I want the 7th, I'm going to add the 6th and the 5th output. If I want the 8th, I'm going to add these two. So you can see how that pattern begins to grow. Is the Fibonacci sequence arithmetic, geometric, and neither? Well, it doesn't have a common multiplier. It doesn't have a common addition, so it's going to be neither. And describe what you would need to do in order to calculate the 100th term. Well, again, recursively, I would have to figure out the 99th term and the 98th term, and I would have to add those two together. So I'm not actually going to calculate it, but that's what I would need to do, is I would need to get the 99th and 98th. As a real quick addendum to this, I just want to add on one thing that I probably discussed in class, although maybe not today, I don't know. Anyway, I never actually saw t of n plus 1 and t of n as a student. What we did was the actual opposite. So again, think about this. If this is t of n, and you want the next term, it's t of n plus 1. So this is this term, this is next, and this is previous. When you're working with t of n and n, you work with this term and the next term. What I dealt with as a student, it was a of n and a of n minus 1, and this is sort of written in subscript. So instead of saying, hey, if you want the next term, take this term, what I was used to was saying something that looked like this. They would say, hey, look, if you have this term, if you want this term, take the output of the previous term and add 5 to it. And by the way, a of 1 equals 3. So you can see it's written differently. It's in subscript. It's not in parentheses. And it's the same idea. They tell you, hey, start at 3. But now it's assuming you're a term ahead. So, hey, you're at this term. So take the output of this term and add 5 to it. And now you're at this term. So take the output of this term and add 5 to it. So you can see if it's t of n and n plus 1 and t of n, we're going to go with this term and the next term, whereas this one works with this term and the previous term. It's very similar, but a little bit different. I just show you this because a lot of the SAT prep and stuff I've seen has a of n and not t of n. And if you understand a recursive sequence, I would hate for you to miss it just because it looks so different, even though it's really the same thing. So again, that's what this equation would look like if we were written with a of n and n. Obviously, the sequence would be 3, 8, 13, 18, etc., right? Well, if I wanted to write it here, I would just say, hey, t of n plus 1 equals t of n plus 5, and then start at 3. So a lot of similarities between t of n plus 1 and a of n. Just make sure you understand those differences.